All right, continuing our series on STEM conversations. I am obviously excited. I'm always excited, but today we have somebody from the James Webb Telescope joining. Name is Dr. Taylor Hutchison, and I am really interested to see how this goes. Zoom is working. Dr. Hutchison, can you hear me?
Yeah, I can hear you.
Oh, fantastic. That is excellent. All right. So, first of all, thank you so much for giving me time to giving some of your time for me to pepper you with some really annoying questions from a random high school teacher. I appreciate that.
No, I'm super happy to talk about this amazing observatory with you.
Yeah. So my son knows more about space than I do, and he's 7. So he named our first dog Olympus Mons.
Aw, that's precious.
So we called him Ollie until he started to attack the neighbors, but let's be on the point.
Mm, mm.
So yeah, so he taught me all sorts of stuff about, like, dwarf planets and all sorts of really neat things. And so then I start teaching high school math, and I'm introducing my students to like different mathematicians and stuff, and I come across Joseph Lagrange. Are you familiar with Joseph Lagrange?
Yes.
Okay, so he solves the three body problem, right? Along with Leonard Euler, and um he gets this famous L2 point. And every time I teach about introduce Joseph Lagrange, I'm like, guys, the James Webb Telescope is floating around a point. Like, thanks to this guy in the 1700s, we're able to spend $40 billion and send a chunk of metal out into outer space.
Right?
So I guess my first kind of question when it comes to all of this stuff is, how much mathematics does it take in order to earn yourself a spot to work with the James Webb Telescope?
Oh my goodness. That is a very good question. I think honestly, it depends on what you want to do with the observatory, right? Because there's people often think of these observatories as, the way they currently exist, up in space, taking data, sending it back down to Earth where we can, as scientists, can look at it and do science. But really, there's so many steps along the way also to get that observatory to that point. And so there's
Right.
so many people from so many different kinds of jobs involved in like designing the telescope, building the instrumentation that goes on it, including all the tiny little pieces that go together to make each of the instruments, and then putting all of it together, doing testing. Something breaks, how do we fix this? And then the people on the other end that are like, hey, government, please give us money so we can make sure this keeps going. And then people on the other end who are organizing, like, oh, hey, we need to make sure that when the telescope talks to us, we can talk back to it. And
Yeah.
let's figure out how that works. So there's so many different things that go into like the generation of the telescope, let alone getting it up into space and using it. And so I feel like it depends on what you want to do. So some jobs will have way more math involved in them, and some will have far less math involved. But
Right.
the stuff that I do, at least, very much math is like a very integral part of it, and just naturally is included in the science that we do.
Yeah, so walk me through kind of like a day. I know this is awful. This is the worst question in the world, and I'm so sorry I have to ask this, but walk me through a day of working with the observatory on your end. Like, I guess I've read your biography a little bit, but it doesn't go into like the nuts and bolts. Like, what
Mhm.
exactly are you doing on a day in and day out basis with the observatory?
Yeah, so I'm kind of more on what we might describe as the user end of the observatory, where I'm way more on the, okay, I've asked the telescope to look at something for me, and it's looked at this distant galaxy and it's sent back this data. And so I'm on the side of where, oh, hey, I have this data. Let me analyze it. Let me see what kind of stars are inside of this galaxy. How old is it? How far away is it? All of this kind of really fun science you can do. And so I'm on the user side of this. But what's really beautiful, especially about working at NASA, is that's as a day-to-day, that's the kind of work that I do. Is I work with the science that comes from the telescope, and
Mhm.
I uncover the mysteries of the universe through that avenue. But I also get to work right next door to the people who are actively working on making sure the telescope's still running. And so I get to have these conversations with people that are like, oh yeah, we just, talked to the telescope like yesterday. We just told it new commands for the week, And
Yeah.
so it's actually really beautiful to work at a place like NASA. So
Ah,
I
that is
do a
cool.
very specific kind of work with this telescope, but I get to have access to a lot of other people.
Right, right. I'm sure so there's a facility there in Maryland, right? That you're at.
Yes, I'm
Okay,
at the Goddard Space Flight Center.
right. And so that building is, I don't want to say that building is dedicated to the James Webb Telescope because I don't know, but that's kind of the hub for everything JWST, right?
It's kind of a mixture, actually. So a lot of the construction and testing actually happened at the Goddard Space Flight Center, but the
Oh,
telescope also kind of moved around quite a bit across the states to the different NASA locations for various testing. Um, so we controlled quite a bit of it as far as the development and testing was concerned. And
mhm,
a lot of the people who are like top leads or in charge of the observatory, like Dr. Jane Rigby, are based at Goddard.
yeah.
But then 30 or 40 minutes down the road at the Space Telescope Science Institute, which is located in Baltimore on John Hopkins University campus, they're the ones that actually have like the control room center that talks to the
Oh,
telescope.
wow, okay.
And
All right.
so we work right next to them, and we're constantly communicating with them to make sure that the telescope is running properly. So it's kind
Okay.
of a joint collaboration there.
So how much coding is involved in your like daily job? Like, so like you're saying that you're sending signals out to the telescope and you're receiving these signals back. Like, how much of it is just like straight like I'm my pea-sized brain, all I can think is JavaScript is the only coding language in the world, but like C++ plus plus for some of us older folks, like
Yeah,
how
yeah, yeah.
how much of it is like coding and sending and just hammering away on coding? How much of it is that? How
I
much you
love that question. It's funny actually. So it's for astrophysicists, you would think that maybe we wouldn't use that much coding, but
right?
actually, my job, the modern day astronomer or astrophysicist, I kind of describe us as moonlighting as computer scientists.
Yeah,
And so we're constantly computer programming. So we use I think the general flavors of languages that people use are the Python
I
coding language,
yeah, that's
which
what I
is
was gonna say. Yeah,
and then, of course, everyone has their own favorite. And so some people will use other options, but Python's the most common one, which is really great because also used in industry and all of this other stuff.
yeah.
Um, Constantly, I'm using it to look at the data. I'm using it to, do my science, make the graphs that I use to show the information that I gather. We are writing our publications that are sharing our science with the community. Most of that's being done like based from Python into this other thing. And so every single day I'm computer programming.
Okay.
You definitely get a lot. It's like the best kinds of math too, because one of my favorite parts of math was always it's like puzzles
Yes.
and you're problem solving and it's puzzles
Yeah.
and computer programming. There's so much of that is the same, like it satisfies that same part of your brain where like
Oh,
you're
that's awesome.
continually finding puzzles and you're solving them. So
Yeah. I mean, there's nothing more beautiful so I want you to go back. Think about when you were in high school. Do you remember learning about systems of equations when you were first
mm,
learning about systems? Do you remember like that that satisfactory feeling of getting a system for whatever reason? Systems of equations does it for me, but just so is it the same? Like you're saying it's the same. Like so when you're dealing with coding and stuff, it in my mind, I don't see it as a puzzle. In my mind, I see coding as like 10 cups of coffee and finding out that it should have been a semicolon and not a colon.
I
So
mean, yes, that happens too,
okay,
unfortunately.
yeah, all right. That's funny. The other thing about coding, and this is it when it comes to coding, and I know that's a big chunk of your job, but do you have your own personal style of writing? So, for example, if you think about like a novel, right? There's John Grisham's style, and then there's like the Twilight style, or whatever. It's still just a novel, right? Or it's still
Yeah.
writing.
Hmm.
Is coding the kind of the same way? Do you have your own style of writing code, or is there just like a systematic, everybody writes in the same style?
No, actually, I mean that's a great point because astronomers I feel are very chaotic.
Okay,
like
good.
like we're not uniform in any way and nothing we do makes sense. Like we don't even name things in a way that makes sense. Like literally as a tangent real fast. So the way that we describe the brightness of objects in the night sky is a system called magnitudes. And the larger the number, the fainter the thing is, which is just a complete flip of what you would imagine.
Why did you do that?
There is a reason, but it's not a good enough reason in my
Oh,
opinion. But
okay,
it's
sure.
100 years old, but like astronomers do nothing that makes sense. And so
Uh-huh.
as part of this computer programming, we're not like classically taught, right? Like I think the only actual computer science class I took was in high school, and it was Java.
Right.
So right. So, and I never used it again, but it did teach you good, like basic skills of like, hey, this is what an integer is. Like, these are numbers, they're called floats or integers, you have strings, which are letters, so those were useful, like, building blocks.
Yeah.
But,
Like if then statements and conditional statements.
everything's different. So everyone codes differently.
Yeah.
There is general discussion in the community of like, hey, please try to like provide notes throughout your code, like
Yeah.
describe what you're trying to do in words, like having some kind of like background information. We have a little visitor.
Yeah.
Um,
Hey.
but no one's consistent, unfortunately. And so there has been some pushback from the younger astronomy community of trying to say like, hey, we should be a little bit better, have some kind of metric in place. Let's be consistent.
Yeah.
But I don't know if that's going to happen anytime soon, because everyone does things differently, because everyone taught themselves how to code.
It almost sounds like this is the Wild West of 2023.
It kind of is. Like, it's definitely, when you teach yourself how to do something, you learn it in a very specific way, right?
Yeah.
And what that means is you get very fixed in your ways because you know how you did it. And
Mhm.
also, you refuse absolutely to learn it a new way or change your habits. How dare you ask me to change my habits? And
Great.
that's exactly what happens with coding, with astronomy.
Oh, that's super interesting. So, are you, there has to be a system of um criticism that's happening, right? Where between your colleagues, you and your colleagues, you're not in school, you're not in high school anymore, so you're not trying to get an A on your next test.
Mhm.
You're trying to discover something phenomenal about the universe, right? So of course you're answering much more complicated existential questions than how do I factor this quadratic.
Yep.
But there has to be some sort of give and take and some sort of like culture of criticism. Like how do you manage being criticized, and how do you manage criticizing others, their ideas, not necessarily them as people, right? I want to be very clear. Like one of my big things in my class is criticize ideas, not people, right?
Mhm.
We're not here to talk about, whether or not, Jimmy likes anime and somebody else likes football. That's irrelevant. What is relevant is, how we're problem solving, and can we be critical of somebody else's ideas to either help them or help ourselves, right? If somebody else has a really good idea, I'm going to take that because I want to be critical of the idea and understand how that idea works so I can use it myself. And also, hey, I saw that you were doing it this way. I found that, you can save 17 steps if you just do it this way. So, and there has to be that culture of critical thinking that you deal with. So how do you accept constructive criticism, so to speak, and giving constructive criticism? How is that dynamic in your workforce?
Yeah, it's a really interesting conversation, because it does, I mean, there's to some degree, right? Especially, I feel like this is the case for any profession, but especially in something like science, it's become such an important part of you, and especially if you've been working on a particular kind of science for a very long time, it's become a part of your identity in a way. And
Mm-hmm.
so, like, first thing that like is kind of said in our community that's like really hard to internalize, but you have to remind yourself of, is like, do not take this personally. Like,
Mm-hmm.
they're not criticizing your abilities as a scientist. Like, if you were to receive criticism, regardless of how it comes, right? Because some people are tactful, some people are not, and that's the nature of the game. But just trying to remind yourself that this is not a reflection on you and your skills and your worth. This is a comment on the work that is in front of you. And yes, you did that work and you put the time into it, and like you cried over it, and sweat and tears. But this is not you. Like, you are separate, and over here is the work. And
Yeah.
so that's the initial way that we try and always approach it. But then as far as providing criticism that's constructive, a common technique that myself and my collaborators use is, at the very least, we have one thing that we compliment or provide like a positive note about, like, hey, if my colleague shows me a graph that doesn't really make sense, or I see the general science point that they're trying to make, but it's not super clear, I can say something like, I really like how you've color coded the different data sets and you've made it really clear and you've changed the shape of the little points. And so I can tell really clearly, just very quickly, which data set is which. And that's incredibly valuable. Now I have some suggestions. And then you can like very like gently say like, oh, hey, so maybe consider, you know, changing this axis or changing the way that you're showing this information. It could be a little bit more informative if you this way. There's ways to constructively bring up those suggestions in a way that won't immediately feel like a criticism in a negative way. But it is a balance, right? That to some
Yeah.
degree is a balance.
So I got a question today in my class. We were looking at patterns and how this pattern grows, right? So it was this little pattern where it's one dot, and then it went to 5 dots and 9 dots, and it grew in it was very basic sequence of events. And a kid asked me, so we were looking at the data like I'm some scientist. We were looking at the way this sequence grew on a graph, and
Mm-hmm.
we're putting together our vertical and our horizontal axis, and it was time and dots, right? So time and dots. And this kid asked me, why do we put time on the horizontal axis? And I
Oh.
went, man. And I ended up explaining it in a way that was satisfactory, and it took me 2 tries, which I was really proud of. Sometimes that'll take a whole class period, but
Mm-hmm.
I don't like letting that kind of a question go. How would you answer that particular question? Why do we put time on the x-axis and whatever else we're looking at on a y-axis?
Yeah, I love these kinds of questions. And I also I feel like I feel you on these kinds of questions, excellent and deep questions that then you're like, oh no, I'm on the spot.
Right. Right.
I so the way I've always interpreted it is, when you have a graph that has an x and y axis, you want
Yeah.
your they would call an independent variable to be on the x-axis. So it's the thing that is, nothing is affecting it. It's the thing that is unaffected, and then on the y-axis is how it's affecting the rest of it. And so time, yes, exactly. And so your independent variable is on the x-axis, which is time. You don't impact time. Time is continuing. We never change time. I mean, there are things in space that could warp space-time, but like we're
Yeah.
not able as humans to change it. And then
This
on the axis, no, exactly. You have the points, and the points are changing with time. That's literally in the sentence. It's changing with time. And so that's why we put it on the x-axis.
You're my kindred spirit. You did it in one try. So what I talked about is, mom has the ability to make a choice tonight on dinner, and you depend on mom making that choice. So
Yes.
mom is the independent here, and you are the dependent.
Her
And
choice
so
impacts you.
exactly. So yeah, that's how I went through and I did my explanation. I'm so happy that you went with it, independent and dependent. That's fantastic. Oh, that makes me so happy. I'm so happy. That's hilarious.
Happy to help.
Yes. All right. So now I got a few like burning questions that every time I think about this, and I just go, no, that's you don't. There's no way. You're using the James Webb Telescope, not you specifically, but you as in NASA. You're the mouthpiece right now.
I am
So
NASA. Yes.
you are NASA right now. You're using the telescope to gather light waves, right? You're gathering light and interpreting that to figure out distances and age.
Mm-hmm.
And in my mind, I'm thinking there's no chance. They're like, how can you tell on like I've looked at the pictures, right? When the first set of pictures came out, super exciting. And of course, I'm like, yeah, clickbait, I'm in. Let me see
Yeah. Right.
all of these. I want to know. And then I'm zooming, and I'm like, oh, look at that spiral. That's got to be a galaxy and all that stuff, right? I'm same exact way, still geeked out about it. But like, how do you know that one is closer than the other? How do you know for sure that this galaxy is 7.4 billion light years away and this one is 9.8 billion light years away? Can you please give me and my pea-sized brain a half decent explanation as to how in the world that you can tell these galaxies are of different distances?
Yeah. Excellent question.
Thank you.
It's definitely very funny. Like space is always a mind-boggling concept to me, even as someone who like has a PhD in it and everything. It feels like sci-fi to some degree. So
Yeah.
this is one of my favorite things to talk about because it still is it's such a challenging concept to wrap my mind around, even still. But so one of the things about space is it is incredibly vast.
Yes.
It is so big. And so as an example, in our solar system, the sun is many millions of miles, millions and millions of miles away from the Earth, right?
Yeah.
Like it's you also could call it the one astrophysical unit, which is a thing that astronomers do.
Right.
But that doesn't give you any information. It's millions and millions of miles. And that's really, really far apart. If we were to have like some evil wizard come through and like, snap their fingers and suddenly the sun disappears, we wouldn't know until 8 minutes later
Right.
because it takes time as fast as light is, 3 × 10⁵ km/s. As fast as light is, it still takes 8 minutes for the light emitted from the sun to travel all the way to the earth and that where we can see it. And so that is even in our own solar system, there is a travel time that light has to have in order to reach us. And so now you can just imagine that's on our solar system. If we're talking about leaving the solar system, staying in our own galaxy, trying to find other stars, that's when we start talking about light years, is because literally it's such a massive distance that light has to travel in a year. And like, so that's why we describe these things in this distance. And so the cool part is because light takes so long to travel, there's this effect that happens in space-time where the light is getting kind of stretched with the fabric of space-time as it travels.
Okay.
So what you're seeing, this is such a small effect in our solar system, and so you don't really see it as much with the light from the sun. But if we were to see light coming in from a distant galaxy, the light, if we want to look at a particular part of light, if you were to describe all light, we would call it the electromagnetic spectrum, which is the very long mouthful word that we use to describe all light. But if you were to take a particular portion, like ultraviolet or something, like what requires us to wear sunscreen, the ultraviolet light coming from a very distant galaxy, or even the Andromeda galaxy, the one that's really near us, it's emitted in the ultraviolet in that galaxy, and then that light starts traveling on its way towards us many millions of years, and it's very fast travel to get to us. By the time it gets to us, that light is actually warped and stretched into larger wavelengths. And so it looks what we would call redder. And so the ultraviolet light, we now see it in the optical, or what our eyes can see. And so suddenly it doesn't look like ultraviolet light to us. But if you were to look at the actual light, you can see very clearly, oh, look, those are things that we see in the ultraviolet. So that gives you an idea of how far away something is. This is what we call redshift. So that's the concept. And so it's literally the stretching of light with time as it travels across really vast distances.
So are you able then, and with the telescope, able to take a snapshot of the wavelengths that come in and study the distance between the peaks of those wavelengths to figure out how far it is apart? Is that,
So
am I
in
getting
a
that
sense,
right?
kind of. And so there's different ways you can do this, right? And so if you looked at just what we would call photometry or imaging, like just taking pictures in different kinds of light of a given galaxy, you can look at the way that the light in that galaxy is changing through all of these different pictures. Like, so if this, if the all the way around me, like imagine a line, I don't know if they'll get to see my hands, but like
Yeah.
imagine a line on either side of me that's connecting. And this is the full electromagnetic spectrum,
Okay.
all light. And we'll call it a light fingerprint for a
Sure.
given galaxy. If we were to take pictures across the entire light fingerprint, so we can see in tons of different kinds of light the way a galaxy looks, you can see the way that the light is changing across these different kinds of light. And this can tell you a lot of information about what's in the galaxy and a lot of other cool stuff, but also that gives you a very unique shape. And so you can tell how far away something is by how much this has shifted to longer wavelengths. So that's one way, is using only pictures. Now, another way, which is my favorite, is something called spectroscopy. And this is where the light fingerprint really comes into play. And you're essentially, if you think of like I don't know if this is dating me, but like the Pink Floyd album cover, where
Yeah.
you have
Yeah.
your
The prism.
yeah, you
Yeah.
have like little like triangular prism, and then like white light comes in, and then the rainbow comes out on the other side, or just
Right.
regular rainbows after rain has happened.
Right.
This is light being what we would call like light dispersion, and it's literally splitting up white light into different little wavelength components. And so you're seeing the range of colors, which is really beautiful. And that's a fingerprint of light. And everything in space and on the ground, everything has a unique fingerprint of light. And if you can get that fingerprint of light through spectroscopy, you can understand a lot of really cool chemistry and physics and science about the thing that you're looking at. And that also gives you very detailed distance measurements, because that fingerprint of light can shift depending on how far away the thing is and how long that light has had to take to travel to us. Does
Okay.
that make sense?
No, that's like in a really fun way. Yes, that is definitely making
Yeah.
sense.
It's really
Yeah.
wild. It's super fun. And
No,
so
it
yeah,
is.
that's
It
how we do
is.
that.
And as you're talking about this, I mean, you have your doctorate in this realm, right? So,
Mhm.
the way I think about people who have their doctorate in some, in some field, they've gotten to the point where they're able to teach themselves some material in a way that they can turn around and explain it to a fourth grader. Right. So like, and that's kind of what I do with my students. I'm like, well, how would you describe a translation, to a fourth grader? Something that here, and then so they struggle, and then finally a kid says slide, and you're like, yes, you're going to slide an object, right?
Yeah, yeah,
So
yeah.
you've had to really spend a considerable amount of time learning some incredibly, I don't want to say far out there ideas, but some ideas that are pretty far out.
Yeah, yeah.
You've had to teach yourself in a way to be able to ingest these ideas as a fourth grader. So you did actually a really good job of describing it. Now, I'm still I'm not gonna lie, I am so not even close to being able to tell somebody else about it, but
Oh,
just
sure.
the idea of being able to explain enough to where I can go, okay, I believe you now. Like I can believe that we are as a community able to say that one galaxy is way closer than the other galaxy, and so I appreciate that. Thank you.
Yeah, yeah.
So more about the telescope. So were you on the team whenever the telescope was launched?
I was part of groups that were expecting like some of the first data from
Okay.
the telescope. I was not part of the team when the telescope launched.
Okay, so I guess the biggest moment then for you must have been when the first set of pictures came back.
Yes, although I was part of I watched the launch with collaborators. It's
Sure.
like 7 a.m. Texas time on Christmas Day,
Yeah.
and we like recorded it because it was actually getting put into a Netflix documentary. Fun fact, but
Oh wow, that's cool.
so like I
Wait,
definitely
were you
cried
on that documentary?
for a second.
Yeah, no, I remember what you're talking about.
Yeah,
Yes. Okay. I made my wife
yeah,
watch that, and she's like, "Why are we doing this?" And I was like, "Cause it's the telescope, honey. It's amazing." All right. So
yeah. So like that grid of faces in that
yeah,
one moment, I'm in there somewhere, looking really tired and worried.
that's amazing.
But yeah, it's like the real event for me then was when that first data downloaded.
Yeah.
And I thought was probably, yeah, the first real event for me.
Yeah. Cool. That's so cool. So you are from Texas, right? And now I have to ask a personal question, and then we can get back to
Sure.
more science. Um, you Dallas Fort Worth area, I believe, is what I read.
Yeah, that's where I'm from.
Yeah. What was your HEB situation?
Oh my goodness. I miss you doing the store, right?
The
Yeah.
grocery store, HEB. Yeah,
Oh, I miss it so much up here. I'm in DC now, right? And this,
right.
but
I'm in
yeah,
Kansas
actually
City, so
in Dallas, there's no HEB. It was there the first time I met an HEB for the first time was when I went to college in near Austin. And
yeah.
so, and then I was like, what is this a glorious place? This amazing grocery store that has everything I need at
Wait,
good
on the
prices.
east, are you talking about the one on the east side of Austin?
Yeah, yeah, yeah.
Yes, yeah. My brother lives like a block away from that place, and I think it's dumb just how amazing of a grocery store it really is.
They're really good at making it an invaluable resource. And so it's so frustrating. And this is such a silly thing to be frustrated by. But now being up here, I have to go to like multiple stores to get the good price on the thing I need.
Yeah,
Um, I was so
yeah.
spoiled and I didn't know it.
Yeah, I grew up in a town south of Houston, and yeah, I mean, there was an HEB my whole entire life growing up. There was an HEB right there, but they've
Right?
gotten better at what they do. It's those tortillas for me, really. They're just the
Oh, no,
ones
I
are
know. I still
so
dream
good.
about those tortillas. I have a
Yeah.
friend who did her postdoc in the Texas area and flying back to, visit sometimes with collaborators. She always packs her luggage with like 16 different packs of tortillas to take home.
Yeah,
So,
yeah, yeah. I also, my mom, like, she accidentally introduced me to brisket beef sausage, and it's an HEB brand brisket beef sausage. So I live in an hour away from Kansas City, and so I miss kolaches, and I know, and so I had to go onto the internets and teach myself how to make kolaches. So I
Mm.
make homemade kolaches. And so every time I'm in Texas or I'm from like anybody comes by that's around there, I make them bring, and this is so dumb, 5 pounds of these sausages.
Oh my
So
goodness.
so I can make my
That's so
homemade.
much sausage.
Yeah, but I mean, when am I gonna be back there? I
I
won't
mean, no,
have
I
it.
fully understand.
It
I'm
sits in my
supportive of
freezer.
this, but
No,
that's a
like
lot of
I don't need
sausage.
all this judgment. I don't need all this judgment from you right now, Doc. Okay. I'm
I'm no
sharing
better though.
I am sharing a very vulnerable piece of myself with you.
I'm like this with the hot sauce actually. There's so many hot sauces. I just cannot
Yes.
find it here. And so what I do is I come back with multiple liters of hot sauce.
Okay.
Like,
So
so you're not
so
alone.
okay, very well. I'm sorry. I digress. For me, as a professional fat kid, everything always comes back to food. So I'm so sorry. Uh,
Love food.
um, so another question that I have is it, do you get to like so do you get to discover new galaxies or discover new stars or new planets or anything of that nature? Like, are you on a team that gets to, or like your own personal like research? Are you like, man, I found a new planet or I found a new, so like my real question is, do you get to name them when you find them?
Yes. So I don't do planet stuff.
That's fine.
That's its own very challenging kind of science, right? But with the distant galaxies that I look at, one of the teams, I'm actually on a number of teams that continually find new galaxies because, this telescope has been anticipated for a decade or more at this
Right.
point.
Right.
And we've been waiting for this telescope because it has better instrumentation, it's more sensitive, it can look further and fainter. And so we can find these really distant galaxies. And so within that first month of data, which I think July of last year, one of the teams I was on, we were very quickly trying to process the data and looking through it and trying to find new galaxies. And one of them that we found was at the time one of the most distant galaxies ever found.
Wow.
And happened to my collaborator, who was the one who identified it, he happened to find it on his daughter's birthday. And so
Oh.
he named it Maisie's Galaxy. And so it's still called Maisie's Galaxy by scientists. Like
Oh, that's
in
so
our
cool.
literature, when we write about it, we're like, oh yeah, Maisie's Galaxy, these coordinates. So
Oh, it's
we
amazing.
can technically name it. We've named a few different galaxies different things. Usually people in our field choose like very long telephone numbers, essentially of like, here's the coordinates and here's like the field it was in. But some
Right.
people do choose to give them special names.
Yeah. So is there a name that you've been holding on to for like that one special, like, I'm gonna do it, I'm gonna find that one galaxy? Is there a
Oh,
name that you're hanging on to so that moment that you find that galaxy, you're like, ooh, I know it. I'm gonna name it Mittens or whatever. Like, I don't know. I'm just
that'd be really fun, actually. I don't know. I feel like a word I really like. So I have a cello and I've named it Avlagloshknik, which is
oh
like
wow.
burning embers in Gaelic. And so I feel like that'd be a really fun thing to name a planet because also it's incredibly challenging to spell. And
Yeah.
I feel like that would just I love providing chaos and putting that out in the universe. And so I feel like that would give me joy. It's like causing chaos.
Yeah.
But actually, one of my colleagues, there's this really cool effect called gravitational lensing, which is where you can kind of think of it as like the base of a wine glass and how light is warping around it.
Yeah.
Black holes do this too, where they warp light around them. But you can have like galaxies, like tons of galaxies close by, have so much mass all together that they're literally warping the light of things behind them. And so it
Oh
kind of
wow.
acts like a cosmic telescope where it's magnifying the light of things that are further away, like all the way around it, and you can see them really clearly.
Yeah.
And my colleague found a star that was incredibly magnified. And actually, recently there's a NASA press release on it. But he found a star that was incredibly far away in a different galaxy. But because of this gravitational lensing or this massive, space telescope on top of our own telescope, he was able to see it really clearly. And he named it after like a Lord of the Rings character.
Oh, that's cool.
It's so there's yeah, so it depends on what you find, but you can definitely like name these things and start a whole trend. So it's the potential is there.
Yeah. Oh, that's awesome. That's really cool. So my last name is Stevens, right? And one of my students walked into class one morning and he goes, "You're the biggest star in the world in the universe." And I was like, careful, that's Steven's son, 18. I'm just Stevens. So let's just get it right. And it really kind of hurt my feelings and made me feel extra thick that day. But
Yes, I am the best star. You could just change
the best.
best
Yeah, just
star.
switch it to the best. Yeah. um I've always wondered, like, if there was, like, if you had to follow protocol when you name it, like hurricanes, right? They have to follow protocol.
Yeah.
Yeah, it's really interesting. All right, that's so cool. I really appreciate your time. This is so much fun. I love it. Do you have time for like maybe a question or two more?
Yeah, yeah, of course.
Hey, cool. So my buddy, his mom, like, I grew up in just south of Houston. Well, I grew up in a town called Friendswood, which is right across from Johnson Space Center.
Oh, nice.
My buddy's mom was one of I think the first female flight director in NASA history. And I talked to her about her experiences, and it was a wonderful, I mean, I really enjoyed talking to her. She's got a lot of really cool things to talk about. One of the things she's working on now is really trying to push more females and minorities in STEM, because when she first got interested in space was when we walked on the moon, right? And so she talked about sending a letter to her congressman, and her congressman at the time in 1969 was like, "Well, young lady, you can't become an astronaut because astronauts have to be from the Air Force, and the Air Force doesn't accept women, so you can't." Well, boy, things have changed, right?
Right.
So she was really on the front wave of like scientists coming through NASA. I guess the first big wave, because before her would have been like Dorothy Vaughan, for example. Do you know who Dorothy Vaughan is?
The name sounds really familiar.
She was part of the calculation team before it was NASA. It was like, oh, whatever the naming convention was at the time. So she was a part of the basics. She was the human calculators.
Oh, yeah. Okay.
And
Yes.
there's a movie called Hidden Figures about her and how
Yeah.
they
Yeah.
took
I do
her.
remember now.
Yeah, she took her team from that into computer programmers. She taught the whole entire team computer programming, just to keep them relevant and keep them employed. And she's just brilliant. But yeah, so there's like a big, like, the history of like females working in STEM, but like at NASA is really a fascinating deal. Have you ever like, so you're kind of later to the party as far as that goes. Do you ever feel like there have been people that had to break down some ceilings for you to get to where you're at? And can you speak to maybe some of the I guess some of the challenges you might have had to face just because you're, a lady scientist versus a regular, I mean, not regular, but like I'm sure there's got to be a good old boys club that you are just like,
Oh, yeah.
get out of my way, I'm here to do my job.
Yes, and that phrase actually, "good old boys club," is a thing we reference a lot with physics specifically. So my undergrad education was actually at this small liberal arts university, like right north of Austin, and it was a tiny physics department that happened to have one astrophysicist, which is excellent because that was my end to get into astronomy. Did not
Yeah.
know I liked astronomy until that moment, but it was great. But then, continuing on, you continually have like this access to like very physics heavy rooms of people or departments that are physics heavy with like some astronomy component. And it's so often you see this good old boys club that happens, and it gets worse because it's good old boys club plus like every like access of privilege you could add on to, right? And so like
Right.
anyone who has any access of marginalization, like let alone just like a gender difference, right? Like it just gets worse,
Yeah.
right? So that's definitely, it's always been a really interesting and frustrating thing to have to work through. I know in my undergrad, I mean, just along gender lines, I was like often the only woman in the room.
Oh yeah.
And there at one point, I was at a very low point in my undergrad. was just struggling so much with the course, and I was asking all the questions in the class, and like I just didn't feel like I understood the material very well. Um, and no one else seemed to be asking questions, and I was like really doubting myself. And then like after the class, I went up to the professor and I was like, you know what, I think I need to change majors, because it's also happened to be my advisor. And I was like, I think maybe, and I was such a bad low point that I was like, maybe they're right. Maybe women just can't do math. And he like looks at me, he's like, don't you dare say that. You're the only one who actually understands the material, and that's why you're asking the questions. And I was like, oh,
Yeah.
got it.
Yeah.
But like it took that. It took, you know, an advisor and a mentor being like, no. Like, here's the things that like are pushing you. Here's like the microaggressions you're facing. Here's the things that are pushing you down. This is actually why you're so valuable and why you're an asset and why you deserve this, you know. And it was a very interesting like frame shift of the way of thinking through it. But yeah, it just, you know, this is, I think, a battle you constantly have to fight with yourself and with others, kind of growing up into this. And so you face different challenges throughout the way, but it is always an uphill battle.
Yeah.
But you know, your goal should always be also trying to, you know, lift others behind you as you rise and leave it better than you found it, in that sense.
Yes. Ah, I love that you said that. Now you kind of hinted at something that I consider imposter syndrome. Do you know what that is?
Yeah, I learned about that in college. I had no idea
Okay.
what that was before.
Do
Yeah.
do you suffer from that still? Like you're
100%.
working on the greatest technological advancement in human history, right? Like
Yeah.
you're doing that. At any point in time do you sit down and go, I'm not good enough. I can't.
Yeah.
Like,
No, exactly. Like I have a PhD in astrophysics. I've studied physics and astronomy my entire like adult career. I've lived and breathed this stuff. I'm part of international collaborations. I have publications that internationally are recognized. I work with like the person in charge of the James Webb Space Telescope, Dr. Jane Rigby. Like I get all these accolades. I still absolutely suffer from imposter syndrome. And what's fascinating is any high achieving person, or honestly just anyone, but like even the people that you assume like would never have suffered with this are also having to fight with their brain and this imposter syndrome. It's just like such a prevalent thing. um and in a way I find that like comforting, in a sense that like everyone's struggling with this, so like you're not alone and you're not isolated in this way.
yeah.
But it is 100% a thing that you
Okay.
have to keep to battle with yourself, and then find ways to push past. And
Yeah.
so one way I do this is I have a list of positive things that have happened like as a scientist in my career, and like positive things people have said to me about my science or about myself as a scientist. And like I just look at that list whenever I'm feeling imposter syndrome pretty bad, and I
Yeah.
call it my readme file.
Oh, read. Okay. Yeah.
And so I look at my readme file when I'm feeling imposter syndrome pretty bad, to remind
Okay.
myself, no, like I do deserve to be here, I'm not an imposter.
Yeah.
So
That's cool. I have what's called a warm fuzzy shoebox. So when a kid writes me a note that's like, hey, thanks, whatever it is, I put it in my warm fuzzy
excellent, that's
shoebox.
your
And I
readme.
can't believe I said that out loud. Like nothing more cringy than a 40-year-old saying warm fuzzies. But yeah, like you know, I don't think it's imposter syndrome as much as like frustration when you're a teacher. Like
Sure.
the bar to become a teacher is a little lower than the bar to become an astrophysicist.
Oh, I don't know. I feel like it's just different bars. I don't know if I could do what you do.
Well, no, right, yeah. It's one of the most painful experiences you could ever go through. Somebody
But imagine
described
like also one of the most rewarding. Like you're
exactly.
you're helping the next generations of people like
Yeah.
explore their life and the world, and like
And
that's such a power and
which
like
is
such a
why
beautiful thing.
1,000,000% why I'm doing this and why I'm reaching out to people like yourself, because my hope is that one of my students is watching and they go, Mr. Stevens, we're in a town of 4,200. We're in rural Kansas, right? We're an hour away from Kansas City. And I'm having a conversation with somebody who gets to use not just like talk about the James Webb. No, you use it. Like you're
Mhm.
answering questions. And so my hope is that a kid sees that and they're inspired to like think outside of the I call the four walls of this town, right? Like
Mhm.
it can do things that are bigger. And this is my community. This is where I'm at. Growing up in Texas and Houston and being here, like I like this is my place now. My kids are growing up here. So like this, I'm ingrained in this community. So but like I want to be able to show them that even though we are here, we can still make connections outside of this that are bigger than us. And so I
Exactly.
appreciate that. I appreciate you being here to help me do that. So STEM, right? STEM is science, technology, engineering, mathematics. You are part of the S, right?
Yes.
So you're part of the S. So when I was talking to Michelle Brecky, who was on the other NASA employee that I spoke to, former, I guess now, she's retired.
Mm,
So I asked her because I think of science, technology, engineering. Science is asking questions and producing experiments to answer questions, right? So that's the way I think about science. Technology is providing new tools to all the other fields around them.
mm,
Engineering is solving problems, real problems, like actual real problems, right? So that's the way I think about engineering. And mathematics is solving more theoretical problems that can then translate to all the other things that we're doing, right? It's the skeletal system of STEM, right? So
truly. Yeah.
when I was talking to Michelle Brecky, as an engineer, I think about what real problem did you have to solve, and she told me this incredible story about how she was in the mission control talking to Sally Ride, and Sally Ride is trying to deploy a satellite, right? And so
Yeah.
she's on the Canadian arm. Sally Ride is on a spacewalk, with moving the arm around and trying to deploy a satellite out of the cargo bay. And Michelle Brecky, I'm talking to her, and she's talking to Sally about doing step one, step two, and going through the algorithm, so to speak. And then all of a sudden, the solar panels don't open, and so she's like, pure panic. Sally's in panic mode. Everybody's like starting to freak out. And so, the problem, she was describing this problem that she had to solve. And one member of her team was like, well, I think the hinges are frozen. So how do you solve that problem? Like, right. So in my mind, as she's telling this story about the hinges are frozen and it can't open up the solar panels, I'm thinking, well, how do you get a blowtorch? How do you get a blowtorch out there to melt the ice and stuff?
Yeah.
And then it dawned on me thinking about how the James Webb Telescope works. Right? You have that heat shield, that 5-layer heat shield, where
Yeah.
one side it's like 45 million degrees. I might be off a little bit. And then on the other side, it's like negative 32 million degrees, right? So it's insane. And so she said that ultimately what they had her do was turn the arm so that it was in the sunlight. And as soon as it hit the sun, like immediately when it hits the sunlight,
Yeah.
the hinges open and everything worked great.
It's like a
Right.
beautiful solution, like a very simple, beautiful solution.
Right. Right. And so okay, so engineering to me is solving those types of problems. So in science, to me, I think you're supposed to be asking questions and designing experiments. What kind of questions are you currently working on? Or what question are you currently working on? And I have a follow-up to that. So I need to remind myself. But what question are you currently trying to solve
Yeah.
or ask? What question are you asking as a scientist?
Yeah. So I have a few questions I would like to think about. But I think my biggest one is, where this telescope is so incredibly powerful. And one of the science cases of this telescope is to find the first galaxies. And so a question I have that I'm working on with others, to try and answer is what are these first galaxies like? Like literally, what is the chemistry inside of them? What kind of
Hmm.
stars are they? Are they the size of our sun? Are they 300 times more massive than our sun? What kind of elements are out there? Is it just hydrogen and helium because it's an early universe? Or do we have things like iron and like exploding stars? And, what kind of black holes exist up there? Are they, millions of times the size of our sun? These are questions you can answer with the instrumentation on this telescope. And so
Oh, cool.
these like literally understanding the nature of the first galaxies and trying to really dive into like how did they get to that point, because then that will help us connect how we got to this point where we are now. And so
Yeah.
that's one of my biggest questions, is just kind of trying to understand that piece of this puzzle.
Are we the youngest galaxy that we know of?
No, but we're actually kind of the opposite in a weird way. Like it's okay. time's also weird in space, right? So this light we're seeing, I described earlier how the light has literally taken millions of years to travel to us. That's why we
Yeah.
describe it like millions of light years away. That means that the light that we see, not only is it been redshifted to larger wavelengths, so it's just shifted on this spectrum, that's how we know how far away it is. It also literally, this is the light that's as of millions of years ago that emitted from the galaxy. So if you were to teleport to that galaxy, it would look different because millions of years have passed.
Right.
But it would take millions of years for the new looking galaxy's light to reach us, because it's this continuous thing, right? So really, like, these first galaxies I'm looking at using this amazing new observatory, they're baby pictures of these
Yeah.
galaxies. And so the fascinating part
Could
is,
they
like,
just not even be there anymore? Could these
yeah, no, exactly. And so the funny part is you have to like add the context of time when you ask that question to me, because the pictures I'm looking at and the stuff I'm studying for these galaxies, these are incredibly young galaxies. They're babies. But if
right,
you were to teleport there, they might not even exist. So
right.
in that context, our galaxy is really old because, it's been forming and been around for billions of years. But if you were thinking in the context of like, okay, if we could just teleport to any place in space, then yes, our galaxy is actually relatively young compared to many other galaxies out there. Because if you could teleport and travel time was not an issue, then the baby galaxies I look at in the incredibly early universe are not that way anymore. They don't look like babies. They're completely old or dead or gone. And so it depends on time, is my really annoying astronomy
Right.
answer.
And I appreciate you. Oh, okay. Because you're trying to, okay. I think of the Earth as a sphere, and I think of the quote night sky as a sphere. And
Yeah.
I know that's probably not great. However, uh you were talking about coordinates, right? So there's some sort of a coordinate system that you have to deal with that's spherical in my
Yeah.
imagination. Am I
Oh
right?
yeah. 100%. You are correct.
Okay. So how do you know where in the night sky that we need to be looking in order to find the earliest galaxies? Or do you not know and we are just guessing? We're just going to keep guessing a trillion times until we figure it out.
Honestly, the way that space-time works and the way that the expansion of the universe works is any direction works. And so literally we just look in any direction, but we do it more intelligently than that, right? Because time is expensive. And so,
Thank you.
yeah.
I'm
So time,
glad we're not just tossing darts.
yes, I
Okay.
promise you, this telescope is, there's some massive telescopes on the Big Island in Hawaii that are like, I think $3 a second to use. That's
Good
the operating
Lord.
cost. The JWST, this massive space telescope, it's more than that. Like I don't know the actual number, but let's pretend like it's $10 a second to use this telescope. So you need it to make sure that you're not wasting time. So, right, just
Gosh,
money.
I'm about to
And
throw up.
so we're not going to waste our time looking at places that would be silly to look at. And so the way that we do this is, the Hubble Space Telescope has peered at these like tiny portions of the night sky for hours. And we have these beautiful deep fields of galaxies. This is where we
Yeah.
see lots of these beautiful pictures. The dark patches in those big, beautiful fields of galaxies, that's where you want to look. You want to
Okay.
look where you don't see something yet. You want to look even further past that. And
Okay.
so we build off of the stuff that we've already discovered or already built data sets with. And so that's one of the strategies is, continually build off of existing data. But then there also are really cool programs that are happening. And I think these are brilliant in that, the cool thing about the Space Observatory is it has 4 instruments, and you can pick one at a time to do stuff. But as one is doing its little science operations and like taking its science and doing its thing and like sending data down, you can potentially use another instrument at the same time. And this is what we
Yeah.
call parallel. And so the cool part about that is there are some scientists who have put in like proposals for telescope time and gotten accepted, where they literally just use that extra little instrument that just stares at random spots in the sky we've never looked at before.
Yeah.
And so they're like slowly building up the catalog of the more part of the sky that we've seen.
Yeah.
And so slowly over time, we'll be actually looking at more and more of the sky that we've not really wasted time looking at
Right.
before. And so this really interesting investment of time in a really clever way, like you kind of get 2 for 1 in that
Yeah.
sense. So we're
So
kind of doing both, but we are intelligent about the choices that we're making.
okay. Yeah, no, I mean, clearly I would assume that the smartest people in the world are not wasting time. But I
Right.
like, that's the stuff that you think about when you're presented as general public guy, you're presented with this technology, you go, wait a second. how did you know to do, you know what I mean? There's a lot
Yeah,
of
no,
questions.
and I love these
Ah,
questions because
you're
honestly,
amazing.
they're great questions.
You're so awesome. Okay, I quit wasting more of your time, and I appreciate you so much for giving me so much of your time. You're being so generous and humoring a lot of my musings of you know, like what to think, what I've been thinking about. And I'm, of course, I have like 4,500 more questions that I want to
Of
ask,
course.
but you know, when you start down this rabbit hole, of course you're like, wow, you know. So I appreciate it. Thank you for being so kind and generous with your time.
Yeah, of course. This was really fun. I had a great time.
Oh well, good. Thank you, and enjoy the East Coast, and good luck getting back to Texas.
All right, thanks.
Bye. Thank you. All right. Bye bye.